said, thanks again, everyone, for being here, joining this webinar. And let's go for what's new in Express 9.5 Solver. So, as you might be aware, FICO Xpress optimization consists of various different components, and they all build nicely on top of each other, nicely integrate within each other, and with your application that you're working on in your company, you might enter the stack that we see here at different levels. Maybe you use one of our business solutions, or you likely develop your models in Express Workbench, our in-house IDE for optimization, deploy them via Insight to cooperate with your colleagues or customers on the cloud. And potentially you develop your models in Moselle or in Python or via one of the various different APIs that we offer. And all of this in the end goes to our Express Solver, which is where I work down here in this deepest, the orange level of the stack, on the heart of Express, the Solver core. And in the next 30-40 minutes, I would like to tell you what news and new features there are to make this heart beating stronger than ever. So, without further ado, let's look into the agenda. I will start with some news on performance improvements that we made to our MIP solver. I will speak a little bit about some new features, some changes in the API before we dive into API and interface updates, and in the end, some performance slides and some announcements that I would like to make. So, MIP performance, let's go. So, in Express pre-solving, MIP pre-solving, we have a feature to reduce the number of non-zero coefficients during pre-solve to exploit equality constraints. So this process involves identifying an equality row, adding it to other constraints where there is a significant overlap between the constraints, and one row and another very similar, not yet identical row are often added to each other, and this then results in cancellations, reducing the number of non-zero coefficients and potentially leading to further reductions. And so building on this, we've now extended this method to column-based eliminations. It's a very similar procedure. You use columns instead of rows, and of course, because columns are, your decision makers and not the constraints, you have to take some extra care here and there. So if a column is free or unconstrained, it can be combined with other columns by introducing new variables that represent the weighted combination of the free column and another column, and eliminating the free column in this way can produce similar cancellation effects as those that you can achieve with rows. So you reduce the density of the matrix and thereby hopefully improve performance of the linear algebra and enable further pre-solving reductions. So this method works for both continuous and integer columns, with integer combinations here being restricted to weights of ±1 logically, so you don't want to spread out your integers or tighten them in. It needs to be like a one-to-one correspondence, literally. And then there are some other pre-solving enhancements. So one of them involves additional coefficient tightenings for models with large big M coefficients. And this process applies an extra tightening step early in the pre-solving phase prior to other pre-solve routines. So this only impacts a few models, but on those that are affected, it has shown some quite remarkable performance improvement. And by the way, that's not only performance. This adjustment also enhances the numerical stability, making it beneficial for models where large coefficients pose challenges. And then as a final update to pre-solving, the pseudo-objective pre-solve has seen some improvement when dealing with all integral objective functions. So in this pseudo-objective, as it is called, pre-solve algorithm, we propagate the objective against the best MIP bound and the incumbent solution value, both in full pre-solving and in the node pre-solve stage. And again, a small set of models is affected, but those see a clear improvement. And another area that we worked on involves knapsack cuts. So for many, many years, the optimizer has included lifted cover cuts derived from knapsack constraints. It's like a pretty standard MIP cutting plane separation procedure. And this traditional approach sequentially lifts coefficients one at a time to strengthen the cuts while keeping their or ensuring their validity. And while this is an effective cutting plane separation, we see that it can be, well, suboptimal in some cases. So yeah, maybe we should look at this from scratch. So how do lifted knapsack cover cuts work? Well, you start with your knapsack row, like you see over here. So less equal inequality with only binary variables and integer coefficients. And when you are given a fractional solution to this row, like this one, here you might be able to identify a so-called knapsack cover cut, like this one over here. So this is a valid inequality because we know from the knapsack constraints that at most one of x2 and x1 can be 1 because the weight of the two together exceeds the right-hand side of the knapsack. But this inequality is violated by this fractional solution, and hence it is a cutting plane. And the solution is cut off by the cut, but it was feasible for the knapsack constraints. So far so good. The task of lifting then is to try and add additional variables into that inequality. So still get a valid but even stronger inequality. So as a matter of fact, looking at the different capacities here, we see that we could also add x3 to that cutting plane with the same argument, or x4 or x5, each of those. And then once we've done that, we are done with lifting. But this, as you see, is it's an approach where it matters with which variable you start. So you get a different cut in the end, whether you start lifting x3 or x4 or x5. The procedure of lifting, by the way, this is also illustrated here on the bottom of the picture. So you see here a cut that's defined only on a single variable. And once you start adding a second variable into it, you kind of tilt that cut and get a stronger inequality that cuts off more of the polyhedron. And here the same thing in 3 dimensions. You start with a cut that's defined on 2, like this one, and add a third variable into it, thereby getting lifted cut. Okay, back to recent developments. So in version 9.5, we've now introduced a more advanced technique for lifting, so-called super additive lifting. So instead of lifting coefficients sequentially, this approach determines, all the lifting coefficients simultaneously, you could say it, by solving an approximate lifting problem. So this enables the generation of stronger cuts structurally different cuts than the sequential method would do, and that might be missed by the sequential method. And this involves solving a more complex problem, but we've used some approximation to ensure that this remains computationally efficient. So in our example, we see that we can actually lift all of the 3 remaining variables together if we add each of them only with a coefficient of 1/2. And this would be a stronger inequality than the one that we've seen before for many solutions. So this would cut off different solutions than the other one. So in practice, we will now generate both super additive and sequentially lifted cuts, and then just the better performing of the 2 cuts is selected because there's no clear dominance between these 2 different approaches. Okay, pre-solving and cuts are always like a bit heavy on the mathematics side. So let's look at heuristics next. So our parallel heuristics have seen some updates. So The Express Solver, since a few releases, employs two different parallelization schemes. Our classic task-based approach that we also use for the tree search parallelization, and then background threads for root node parallelisms that we've introduced something like 3 years ago or so. And those background threads, which are enabled by default, handle various different jobs, such as large neighborhood search heuristics, some fast feasibility heuristics, and more during the root node processing, running, as the name suggests, in the background. So not much interacting with the cutting loop. So this background scheme has little synchronization overhead, but exactly for that reason, it also loses some potential for the heuristic performance, because new solutions from the foreground do not get communicated to the background, and background heuristics among each other do not communicate. And at the same time and independently, we still have the heuristic threads, the heuristic threads mechanism in place, which allows us to execute parallel heuristics in the foreground with much more interaction with the remaining search process. It's a non-default procedure, and this interaction uses the same parallelization scheme that we use for the tree search and works via synchronization steps. It is well, of course, deterministic, and it is, as it is with deterministic parallel algorithms and synchronization. The more synchronization, the more potential is there for idle time, and this might lead to some bottlenecks. And in the past release, we have systematically identified such bottlenecks in the specific case of heuristics and improved the synchronization for this specific use in the heuristic context, and it achieved to cut down the overhead in this Euro-threads framework by a factor of 2. So we cut the overhead, synchronization overhead, into half, essentially. Anyhow, using parallel foreground heuristic continues to be a non-default feature, but users who already were using it might expect some performance improvements, and for others with some heavy heuristic focus on their problems, this maybe becomes a viable option now where it hasn't been before. However, keep in mind that the first thing that we always recommend for heuristic heavy problems is trying Euro emphasis equals 1, and after that, using non-default heuristics might be a secondary step that you might want to try. Okay, another update involves our barrier algorithm. So here we have a new starting point heuristic that we introduced that improves pure barrier solves, including crossover stacks by the crossover step by about 7% on hard pure LP instances. This feature is off by default for now, as it has some mixed effects in the MIP context. So user can enable it manually if desired, and if you're a barrier user, again, this might be something that you might want to take into consideration. And then finally, we went through some internal refactoring, which is not unusual during a development process, but I think one thing I would like to mention today is that this time, besides others, this involved revisiting all our uses of sorting algorithms internally, which seems like a minor detail, but here this yielded some quite measurable performance gains pretty much all over the board. So in this process, also our symmetry detection has been made more effective, reducing its runtime by about 60%, which is really nice. And finally, we could systematically improve our handling of out-of-memory situations in some rare occurrences of memouts. Okay, let's look after these performance views, after the mathematic point of the site, a little bit more into the new features, the new API functionalities that we offer here. So I should put a little disclaimer here. All the API functions here are from our C interface, but of course this also applies to other interfaces just with different capitalization mainly. So in terms of solution handling, we've introduced some new unified API functions for getting information about dual and primary solutions inside callbacks. So namely the Xpress get callback solution, or Xpress get callback slacks, or get callback duals, red costs for reduced costs. And so these functions retrieve the context-specific solutions for the respective callback they are called from. So if you take the Xpress get callback solution function as an example and consider this cheat sheet over here on the right-hand side, so what you would understand as a solution really depends on the context of the callback. So is the callback an iteration callback of a continuous solve? Well, then solution refers to the current iteration solution. So potentially fractional point, not necessarily feasible, not necessarily optimal. Is it an integer solution callback? Well, then the solution obviously refers to a newly found integer solution. While in a pre-install callback, it would only be a candidate solution. Branching or an opt-node callback, well, then solution probably refers to an optimal LP solution. So this approach here replaces some less consistent methods of how you would exactly retrieve the solution that you're looking for in each of the various different callbacks. And that simplifies the process for developers. So you do not actively have to think about what exact kind of solution or candidate or iterate you need to request in the callback type that you're currently working on with. You call Xpress get callback solution and get from it what you would expect. So also importantly, these new functions work seamlessly across MIP, Global, and SAP Solve. It's the same everywhere. And for advanced users, additionally, you can access solutions in the pre-solved space using a corresponding Xpress get callback pre-solve variant. So Xpress get callback pre-solve solution slacks and so on. Consequently, legacy functions like Xpress get LP solve will eventually be phased out as the new approach offers a cleaner, more consistent interface here. And for those working with array dimensions, new attributes, like if you're using the C interface, new attributes like input rows and input calls provide problem size information directly, thereby hopefully further simplifying the user experience here. So in summary, avoid using Xpress get LP sol, Xpress get MIP sol down the road and use the new functions and callbacks, or get the general Xpress get solution for the best solution after a solve. And yeah, as I said, disclaimer down here. I use the C language as an example because that's the solver's native language, but it really works in all other languages as well. Okay, then there are some smaller updates that enhance the functionality that we offer and also our logging. So features like Xpress at MIP solution and Xpress fix MIP entities are now also supported by our global solvers. Hence, when you solve MINLPs, convex or non-convex, or NLPs, convex or non-convex, to proven global optimality with our built-in Express global solver, you can then use these functions to add a reference solution before the start of a solve, or to fix all integer variables to resolve the remaining continuous problem. So you just should keep in mind if you use Xpress fix MIP entities and then solve the continuous problem, again, that for non-convex MINLPs, continuous problems can be hard to solve and even involve a branch and bound search of its own. So then for expert users, we have made some of the sparse linear algebra functions publicly available, namely Xpress sparse ftran and Xpress sparse btran, that fulfilled the customer request that we had. So if you are a simplex aficionado or you like implementing your own Tableau-based cuts, then here you go. Note also that the dense versions of those functions continue to exist. So it really depends on your use case, which of the two you find more useful. And don't be worried if you don't even know what an ftran or a btran is, that's just fine. Then this is just not the functions for you. Okay, what else? When computing an irreducible infeasible subsystem, so when you had a MIP or an LP that was infeasible, and you want to get the information of which constraints, which variable bounds are responsible for the infeasibility, then instead of only retrieving the set via an API, you can now also print it directly to the log. This is just a nice little convenience addition. And then finally, primal and integer violation are now also printed in the log for global solves. So previously this was exclusive to MIP and AP solves. Now also for nonlinear solves you would get this information about primal and integer violations. So I think what you can see here is that one theme of the slide is that with the global solver, you can now do almost everything that you can do with the MIP solver. We are closing the remaining gaps in functionality that's offered for global MINLP solves. So, okay, let's look into some new APIs. So already in Express 9.4 in April, we've started to new augmented APIs for Java and C#. So these new APIs provide a new, efficient, intuitive, object-oriented modeling experience. They support all the solver features and modern language constructs from each of the languages, provide a consistent user experience across the different programming languages with a very consistent and intuitive interface. And this now also includes C++ on top of Java and C#. So today I will only give a very high-level view. Much more details will be given in an upcoming webinar next week by my colleagues. So the design of the augmented solver API addresses the dual ways that optimization problems can be represented. There's on the one hand the matrix view with rows and column indices working with arrays. And then there's the algebraic view of the model, which focuses on the semantics of the problems. So with their constraint classes, their variable types, there's object orientation, and so on. And while the matrix view is highly efficient for computations and memory usage, so what I, as a developer, like to do, it's normally less intuitive for modelers. So conversely, the algebraic view is much more human readable, which is nice and easier to maintain your models, but it's less efficient in terms of speed and memory consumption. So to bridge this gap, the new APIs unify these two approaches, offering the best of both worlds, really, while in addition integrating programming capabilities for data processing and deployments. And this holds for all languages: Java, C#, Python, and now C++. So the new interfaces introduce a unified and object-oriented modeling framework that enhance readability, maintainability, while still supporting the matrix-oriented modeling, if you wish to do so, and the full solver interaction as an underlying layer. Okay, so this is in a sense the top-down UX view. So let's look at some of the technical details now in a bottom-up manner. So how is this implemented? Well, the Express Solver in its core is written in C, where it naturally uses a matrix-oriented approach for maximum efficiency. This also holds for its C API, the native API of the solver, if you wish. So everything is matrix-oriented there. I mean, fair enough. C is a very low-level language without really a notion of objects to begin with. And the new API architecture first then puts a thin API layer on top of this in all the languages, directly wrapping the solver's C functions and being publicly usable if you want. So for Java. This uses the Java native interface. While for C++, it's implemented with classes that use exception-based error handling, as you would expect as a C++ user. So this layer remains matrix-oriented and, well, would require users to work with indices if they want to work with this. But really above this layer, in the second layer, you have the object-oriented layer that translates indices into objects like variables, expressions, constraints. So this is the augmented level that you normally would want to use, and where you don't even need to know about all of the underlying levels. So I'm only telling this for technical curiosity here. So any changes that you would do in this level, so when you use this here for modeling, they are directly reflected in the underlying solver, so things are always kept in sync. So the data is really unified in the lowest C level. So if you wish, you can mix and match using lower and higher level API functions. It's of course not really recommended unless you have specific reasons to do so. And what else? Yeah, importantly, all the yellow part here, really all of the yellow part, is implemented with managed memory in Java and C++, with smart pointers with managed memory in Java and C#, smart pointers in C++. So you have memory management in place everywhere. So everything there with respect to memory is automatic, nothing that you have to worry about as a user. So you can learn about all this and get a live demo of how seamless coding with our new augmented C++ API works next week. Same day, same time, but a different Zoom room that you need to register for independently. And I believe Jens already posted a link into chat. Okay, then let's talk about some news from Python and Julia. So one of the most notable updates that we have to our Python API in this release is the support for SciPy sparse matrices. So a feature that has been requested by our community multiple times. We listened and implemented it. So SciPy sparse matrices are some quite efficient data structures for handling matrices with predominantly zero values, and address the inefficiency of using dense NumPy arrays, for example, or using manual loops there, because previously, if we were forming sparse constraints, this required some iterating through data manually, which is cumbersome and computationally expensive. You don't really want to do that. So users can now directly use SciPy sparse matrices to create constraints, and operations like multiplying a sparse matrix with a vector of variables now scale with the number of non-zero elements rather than the total matrix size. So this offers some significant performance gains if you're dealing with huge models. Yeah, all of this simplifies sparse data handling and avoids resorting to the lower level index-based API that we've just mentioned. So in 9.5, we support two sparse matrix formats, the row major and column major form, as it is called in the SciPy lingo. And another enhancement to the Python API touches again on our solution execs functions. So functions like getSolution, getSlex, getDuets have been renamed for consistency with the solver's naming convention. So these functions are also now implemented directly within the solver, and Python just interfaces them and ensuring again some consistency behavior. So the legacy functions will retain their original names for backward compatibility, but they are marked as deprecated. And speaking of which, a new deprecation mechanism has been introduced in the Python interface specifically. So Python will now emit runtime warnings when you use deprecated functions using Python's standard warning module. So yeah, check for those warnings during upgrades. Use the recommended replacements to future-proof your code. Okay, Also, we released as a nice side project, so to say, a new low-level Julia API, which is just a simple wrapper around the Express C API. So when you remember the nice orange yellow graphic that I showed 2 slides earlier, for Julia, at the moment, you only get the middle part, the matrix-based API, but no augmented object-oriented modeling level. So it's a thin wrapper. This Julia API is available via GitHub, and it's part of the official Julia registry. And again, for some more details on Python and Julia, I refer to the webinar by Susanne and Bruno in 2 weeks from now in yet a different Zoom session. And yeah, slowly nearing the end of the presentation, let's look quickly at performance numbers. So this is our typical year-on-year improvement table that we always show in these webinars. So a year ago, the current Express release was 9.2, and this table compares our new 9.5 release against 9.2. So these are numbers on our internal benchmark set consisting of a mix of public and client instances. Client instances here are sampled to avoid any type to dominate the benchmark, and we compare geometric means of runtimes here, except for the PDI row, where we compare the so-called primary dual integral. That's a measure for convergence of the primary and the dual bounds. And we look at geometric means. So we see that the mid improvements this times are a little bit shy of the typical 15 to 20% that we often report in these webinars, whereas our nonlinear improvements are really strong. So there's a factor of 3.3 on our global MINLP benchmark. And while the global solver is still a relatively young solver, so it's 2 years old now, I think it's fair to say it's growing up, and this is a really strong, nice number. This is also witnessed by our convex quadratic numbers. So convex quadratic solver is a very long-standing solver, but still this time around it saw a speed up of about 40% on hard models, which is quite nice. Okay, finally, I would like to make some announcements. So first of all, there's the FICO Xpress Best Paper Award, which is an academic award that acknowledges outstanding papers in the area of ORs and optimization and related fields under the condition that you used an Express product somewhere inside the paper. Comes with a nice prize money, and as an entering condition, the paper must have been published in a peer-reviewed journal or a well-refereed proceedings. The submission deadline for this third edition of the award is the end of January, so there is still some time to prepare and submit your paper. If you've got something in the pipeline, please do so. Always interesting to look into the research that people are working on. At this point, I would also want to congratulate again the winners of this year's FICO Xpress Best Paper Award, Giorgio and Joanna, with their work on the feasibility jump, and we also had a very nice runner-up paper from the team at Amazon Research. Earlier, well, not earlier this month, like in the middle of last month, we released 2 blog posts explaining in detail the research that those teams worked on. Very nice reads. So where can you find those? Well, on our FICO Xpress community page. A link should also go into chat together with the page on the FICO Xpress Best Paper Award. So these are ways of reaching us. Check out the FICO Xpress community, where you would also find a free community license, quite active user forum, or blogs, both our internal and some external blogs revolving around Express. And if you're an academic, then you are certainly interested in our FICO Xpress Academic Partner Program, where you can get fully fledged licenses for free for your academic research and use for teaching. And as a final announcement, there's a new MINLP coming. So MINLP is a collection of open instances, mixed integer programming instances for academic research. People at ZIP are currently collecting this. The deadline has been extended to the end of the year. So if you have some MIP models that you would like to share with the general public, that's a way how you can do so and get some visibility. And yeah, before closing off, I would like to point to the upcoming release webinars. As mentioned before, there will be 2 more before Christmas. So this is Daniel and Alex with a webinar on our augmented C++ API, and Susanne and Bruno elaborating on Python, Julio, and Moselle. So with that, thank you very much for your attention.